Okay, let's dive right into this. Welcome to the Explainer. Today, I want you to put on your researcher hats with me because we are observing an absolute evolutionary leap in artificial intelligence. For the past couple of years, we've seen models get incredibly smart, but they've kind of been trapped, right? Trapped in these isolated sessions. You ask a question, you get an answer, boom, the session ends. But what happens when agents need to run for hours, or literally days at a time, working right alongside hundreds of other agents in a massive enterprise environment? To pull that off, they need a true cognitive architecture. They need to evolve. So we're going to explore the brand new capabilities of agentic memory in this fascinating research preview called Dreaming, which, spoiler alert, radically improves both enterprise agent reliability and cost efficiency.
So here's the core research question we have to tackle today. How do we teach an AI to remember, and more importantly, to dream? Because as it turns out, continuous self-learning agents, they just can't operate in a vacuum. I mean, if an agent is managing an entire codebase, or maybe acting as a site reliability engineer, it has to learn about its environment. It needs to track what works, what utterly fails, and what all the other agents are doing. Building a system that allows an AI to maintain that kind of context over a super long horizon task requires a massive, fundamental shift in how we handle data. Section 1. Anatomy of Agent Memory. Dissecting the AI brain.
Let's open up the hood here and see exactly how this frontier memory system is structured. To build a continuous self-learning agent, Anthropic realized they needed to model memory in distinct layers. First up, the storage layer. And look, this isn't just dumping raw text into a database. It's storing the core data right alongside rich metadata and attribution. We're talking tracking exactly which agent made an update, at what exact time, and in which specific session. Next, we have the content layer. Now, rather than boxing the AI in with rigid, clunky API calls, they took a really brilliant approach. They gave the AI memory in the form of a file system hierarchy. State-of-the-art models are already fantastic at using familiar developer tools, things like Bash and grep, to navigate and manipulate files, right? So by structuring memory as a file system, the AI just naturally knows how to split files, organize data, and retrieve it. It's like giving it a digital filing cabinet it already knows how to use. And finally, the process layer. This simply dictates how often memory is updated, what actually triggers those updates, and what sources the agent uses to learn.
So the crucial point here is perfectly captured in this quote straight from the developers. A swarm of agents building up their own understanding, their own model of the world that they're in over time. When you have all these layers working together, you don't just have a standalone chatbot anymore. You have an entire multi-agent system. A swarm of agents all working in the exact same environment on discrete tasks, but they begin to collectively evolve. They share what goes wrong, they share their big wins, and they build a truly unified dynamic model of their virtual world. Section 2. Preventing memory collisions. The nervous system at scale.
Now, of course, sharing a brain introduces a really massive logistical headache. Think about it. What happens when hundreds or even thousands of agents are reading and writing to that shared memory simultaneously? In a high-stakes enterprise environment, a collision where one agent accidentally overwrites another's crucial data? That could be catastrophic. So, to prevent this, the architecture uses something called optimistic concurrency control. This is a clever mechanism that uses a preconditioned content hash to ensure parallel agents do not clobber or overwrite each other's shared memory. It's an elegant safeguard that essentially acts as the ultimate traffic cop for the whole agent swarm's nervous system.
Let's actually walk through the exact mechanical sequence of how this traffic cop works. Step 1. The agent learns something new and prepares a memory update. Step 2. Before that update goes live, the system checks the preconditioned content hash. Step 3. It verifies that the memory state hasn't been changed by another agent in the split second since this agent last looked at it. And finally, Step 4. Once verified, the memory is safely updated. And what's really fantastic about this strict step-by-step sequence is that it gives enterprise developers complete control, plus a highly granular version history. Every single change has a detailed audit log. You can literally go back in time, see exactly which agent altered a file, why they did it, and exactly when.
Section 3. Mimicking Human Reflection, the REM sleep of AI.
Now, what's really fascinating about this next slide is the stark contrast it draws between two completely different states of AI awareness. This is where the whole cognitive architecture starts to sound, well, incredibly human. To understand why dreaming is so necessary, just look at the difference in perspective. A single agent perspective is highly localized. It's siloed. If an agent is actively grinding away on a task, fixing a bug, or answering a user prompt, it only has the limited perspective of its own real-time context. It's on the hot path, right in the thick of it. But the dreaming process operates entirely differently. It is an out-of-band, batch asynchronous process. And because it runs quietly in the background, entirely separated from the hot path of those real-time tasks, it doesn't add any latency. Instead, dreaming kind of steps back, takes a breath, and looks across the entire swarm of agents, analyzing multiple sessions to identify overarching macro patterns that a single, busy agent would literally never be able to see.
You can almost think of this as test time compute, where an AI intentionally spends extra tokens to reflect and improve. As researchers observing this digital organism, the outcomes of this REM sleep cycle are just profound. During dreaming, subagents review recent transcripts and achieve some incredibly critical optimizations. They identify common mistakes, like, say, a specific tool call that constantly fails for multiple agents. They discover shared strategies that are actually working well. They deduplicate redundant memory entries, so if 5 different agents learn the exact same thing, dreaming consolidates it into one nice, clean file. It completely clears out stale or irrelevant info, and my absolute favorite part, it adds verification notes. It literally leaves a note for future agents saying, hey, I've reviewed this transcript, and this memory is accurate and verified. It is self-curation at a massive, massive scale.
Section 4. Configuring the dreaming process. A researcher's guide. So, if we actually want to run these highly intelligent swarms, how do we manage their sleep schedules? Well, the life cycle of a dreaming job is highly configurable for enterprise developers. First up, the trigger. You can kick this off on a schedule using a cron job, trigger it manually via an API, or just have it automatically run right after a major task spins down. Next is the ingest phase. The system will gather up and review the input session transcripts, for example, looking at literally everything the agents did over the last 7 days. Then comes the process phase. The system automatically spins up subagents, whose sole job, their entire purpose, is to read through those transcripts and identify those shared learnings. Finally, the output. The dreaming job produces a diff, which is basically a set of updated files. As a developer, you can choose to apply this diff immediately to your memory store, or you can route it through a standalone API for a manual human review or maybe sensitive data scanning before it actually goes live.
And this brilliantly illustrates exactly why dreaming is such a game changer. During early testing, developers spun up an SRE agent, a site reliability engineering agent. By reviewing multiple transcripts across all these different alerts, the dreaming process noticed a really insidious hidden pattern. It identified this highly inefficient 60-second retry loop that was kicking in after an upstream CPU spike. Now, the individual agents who were all rushing to triage their specific alerts completely failed to notice this systemic delay. They were just too close to the problem. But the dreaming process saw it across the entire swarm, documented it, and essentially left a digital sticky note for all future agents saying, hey, don't bother with this loop, we already know it fails. That kind of self-correction, it saves massive amounts of time and compute tokens.
Section 5. Enterprise reliability and efficiency. The evolutionary leap.
All right, we've talked a lot about the architecture, but what does this actually mean out in the real world? How does this cognitive leap impact tangible business metrics? Well, the results from early adopters are simply staggering. Rakuten deployed this exact memory system for their internal knowledge agents, and they saw a massive 90% drop in first-pass mistakes. 90%. Think about that. Because the agents were able to constantly catch mistakes, share them through that unified memory store, and apply those learnings to the very next iteration, the entire system became vastly more token efficient. For an enterprise, that translates directly to significantly lower costs and much, much better latency.
We also have some incredible data from Harvey, who tested out the dreaming process on realistic legal benchmarks. By allowing the system to run this batch asynchronous reflection, they saw a 6 times increase in their task completion rate for complex legal scenarios. A 6x improvement. It makes perfect sense, right? When an agent doesn't have to start from scratch every single time, when it actually has a highly curated, verified index of shared intelligence built by its peers, its performance absolutely skyrockets.
Let's move to our final point and see how this builds a completely new paradigm for our technology. Continuous self-learning. We are no longer just prompting a model in a vacuum. We're orchestrating true agents that can run for days at a time, safely sharing state and building their very own evolving models of the world. Through file system memory and this asynchronous streaming process, we are literally giving AI the tools it needs to self-optimize. Which really leaves us with one final profound question to consider. As these multi-agent swarms continue to dream, iterate, and completely rewrite their own shared reality, what exactly will they learn to solve next? Thank you so much for exploring this explainer with me today. Keep learning, and I'll catch you in the next one.